All right, we're going to start our discussion on the double integral in the polar coordinates. And here, obviously, we want to build upon the knowledge we just discussed previously about the conversion between Cartesian coordinates and polar coordinates, and how to represent the um, curve given in the Cartesian coordinates um, and to represent by using the polar coordinates. And those will be very useful. But here, let's just introduce one thing, one example to illustrate the ideas what we're going to do about the polar coordinates in terms of double integral. Okay, we want to evaluate or set up actually, because we're making it more abstract. Set up double integral or this abstract function f with domain of the integration d being enclosed by circle of radius 2 centered at the origin. All right, and here I think we solved this before by using the double integral and the iterated integral that we discussed all along. Oh, if you remember, this is what we obtained. Okay, there. And here we want to make a little twist. We're going to do the same thing, but we're going to ask to set it up in polar coordinate. Okay, so this is what we're going to do. But before we are able to do that, we have to really introduce the double integral or the iterated integral in the polar coordinates. So this is what we're going to focus on right now. Okay, so what is the double integral in the Cartesian coordinates? Well, hopefully we all remember this. This is what we have, right? So the important part we want to emphasize here is a differential of area is indeed either dx times dy or dy times dx, depending on how you treat the domain integration d as type 1 or type 2. All right. And here we want to see how do we obtain the double integral for the in the polar coordinates. And the idea is this. So suppose we have the domain integration denoted by this letter r, and as we build the double integral in the Cartesian coordinates, we're going to divide this big fan region or pi region into a small pieces. Well, each of those small pieces will have roughly the same shape as the bigger one. And what we are going to do is that we are going to use the polar coordinates to represent the area of each of the small pieces around those points. Okay, remember this. We can zoom in over here, and we can try to see what is the area of this small piece. Okay, by using some algebra and analysis, especially taking advantage of this readings and the circular region, and we can see this side is r times d theta, and then this side is dr. So roughly this area dA is indeed is r times d theta dr. So this actually gave us the approximation of this area element for the double integral in polar coordinates. Okay, so now we can set it up. The important setup is um, done for the so-called the polar rectangle. So we restrict the R between two constant A and B, and we restrict the polar angle theta to be between two constant alpha and beta. So this is the polar rectangle, right? And for this double integral over this polar rectangle, or this function f of xy, is the differential of dA. We're converting this literally one by one from the Cartesian to polar. And obviously over here, if we decide we're going to write our double integral in the polar coordinates with the order. So here we want to point out, let's use a different color. So here dA is converted to r dr d theta. If we do this conversion, then this is the exterior integral. We have the theta variable to be integrated. So it is between alpha and beta. And for the interior integral, we have the integration variable r, and then this r is between A and b. And this dA is completely replaced by r times dr theta. Then we essentially get our double integral set up in this polar coordinates. Another thing is, remember x is indeed r times cosine theta, and y is converted by using r times sine theta. Then in this iterated integral over here, we have all just r to theta. So this is what we're going to get. So the key in converting this double integral in Cartesian coordinates to this polar coordinate is to recognize this. Okay, so either dA is becoming r times dr d theta, or dA is becoming r times d theta dr. So either way. So here, we have to pay attention to this conversion, and obviously the Cartesian the polar rectangle is the most simple case, and just like the general double integral in Cartesian coordinates, we could have, for example, this interior parts, this interior integral, which is for the integration variable r. We could allow this r to be having a variable lower and upper limit, which depend on the value of a polar angle theta. And then this is most likely what we're going to see in our double integral calculation in the polar coordinate. Okay, so this is the setup, and the key is to remember dA is r, there's actual r times dr d theta, or r times d theta dr, depending on your order of integration. Okay, so with this, how about we go back and work on this question. So we know for this one, the double integral over d and this, right? So and we also know this domain D is the region enclosed by circle radius 2, and I think we know how to represent this D in terms of polar coordinates, which is All right, so now we know r x has to be replaced by r times cosine theta, and y has to be replaced by r times sine theta. And the trick is, what is the dA is becoming? So here, if we choose dA to be equal to r times dr d theta, then we can copy r times dr d theta here. And then we also determined the order of integration. So the exterior integral is for the theta variable, which is running from 0 to 2 pi. And the interior integration variable will be for r. So r is between 0 and 2. So this is what we are going to get. So for this conversion, we can see clearly the most important part is we have this extra one. And r times f together is becoming the new integrand in the polar coordinates. Yeah, so this is the first example we want to emphasize. And there is another one. Let's see. Well, how about we do this? How about we do this problem first? And what do we want to do is we want to first evaluate this double integral in polar coordinates. Well, evaluate and explain. We first want to evaluate this, right? So how about we evaluate it first? If we want to evaluate this, what we are going to do? We have to be sure this is for theta, and this is for r. Okay, so we can just evaluate this first to see what we're going to get, and the theta is between 0 and pi over 2, and the integrand, well, we are integrating about r, right? And the integrand antiderivative for r is r squared over 2, and here r is evaluated at 0, and well, the upper bound is a function of theta. So this is what we have. Now we can continue. So we get 2 cosine theta squared over 2 minus 0 squared over 2 d theta. This is becoming what? This is becoming 4 times cosine squared theta over 2, which is 2 cosine squared theta, or theta between pi over 2 and 0. And here we want to talk about the trig identity. How do we integrate this? So if we want to, there are a couple ways we can do that.